So, just a couple of things to remind you. Master Chemistry Chapter 5 Part 1 was due on last Wednesday. 5 of you chose not to participate in that assignment and didn't do it. A couple of you didn't do much of it, but that was the short one. The assignment that's due this Wednesday is Master Chemistry Chapter 5 Part 2. It's 15 problems, much more involved in assignment, but we'll finish up Chapter 5 today. I'll get Chapter 6 posted, and it'll be due probably less than a week. Chapter 6 that we're going to start next, thermochemistry, is a little bit shorter chapter compared to what chapter we just did, so we'll go through it fairly quickly. So just things to think about in terms of the progression of the semester. This is week 10 of 16. So exam 3 is not going to be that far away. The semester's taking long. So we're fairly on track with the amount of material we need to do. I don't have the lab posted next week or for this week yet, so I've got to talk with the other faculty members and see what we're going to do in terms of a lab experience, but we'll figure that out, which path we're going to go. Okay, so the last thing we talked about was looking at stoichiometry and relationships we can calculate with the ideal gas law. So we're going to continue now with towards the end of the chapter, and we're looking at some concepts and properties of gases and the characteristics that we see of gases and how we can relate that to the things that we learned with the ideal gas law. So we know some properties of gases is that they expand to fill the container regardless of what the shape is. They spread out and take that shape. Usually gases have low density that are considerably lower than that either of a solid or a liquid. Remember, we talked about the densities usually described in units of grams per liter instead of grams per milliliter with gases. And then if we have a mixture of gases, they behave as one type of a system. So it doesn't matter that there are multiple gases there. We talked about Dalton's law of partial pressures. It's like there's one phase that's there. And gases are compressible to the point where they convert into the liquid. So the kinetic molecular theory is a concept that looks at describing the motion of these gas particles. And it's our simplest model to describe what we think that's actually going on. So in this theory, we treat a gas as a collection of particles, whether it be from molecular species or from atoms, that are in constant motion. So there's no gas particle ever sitting still in this idea. They're constantly moving in all directions, and they're moving in straight lines until there is a collision. So you have this one coming in and this one coming in, they hit each other and they bounced off. That's our concept. They're always, it's bees in a jar moving around, or however you want to think about that to something in nature. So with this, if the particles are in motion and they're constantly moving, the assumption that we're making is that there's not much attraction between the particles. If they go by each other, they just fly right by. If they actually hit head on, then they bounce right off. And the idea is that the way they would bounce off is something like a billiard ball. All right, so billiard balls hit, there's a conservation of momentum. So you can have them to two things. If they hit dead on, they'll actually bounce back away from each other. Then they slide off at actions at different angles. A lot of physics involved with playing pool, but we think that's the concept that we have, the way these gas particles move. Now, the main thing about gases is that we compared it to something like the solar system model we used to describe the electrons around the nucleus. Gases are mainly empty space. They can move a long ways with the relative size of an atom before they run into something or they hit the container. So they have this opportunity to move around great distances. So what the kinetic molecular theory says is that the average kinetic energy of a gas particle is directly proportional to that temperature in Kelvin. So as we raise the temperature of a gas, the average speed of the particles increases. Now, when we say this, the key thing to remember is that not all the gas particles are moving at exactly the same speed. We'll address that in another slide. So the idea that we use to describe the collisions that occurs between the particles or the wall of the container is we use the term is that they're elastic. And if collisions are elastic, that means there may be an exchange of energy, but you don't lose energy. In particular, the type of energy we're talking about not losing is kinetic energy. So I want to insert the word kinetic here. The kinetic energy is conserved in this. So if you think about what happens if you have a pool ball here and another one coming in, so this one has motion, it's going to strike this one. This one has no motion, so this one has some velocity, initial velocity. This one has initial velocity equal to 0. And then after the two hit, maybe this one goes off in this direction, and typically its velocity is going to be reduced. The mass stays the same, but now this one's going to have a velocity. And the equation that used to describe kinetic energy is 1/2 times the mass times velocity squared. You've seen that in physical science or somewhere else. The mass stays the same, so what's changing here is the velocity. So what elastic collision means is that the summations of the kinetic energies stay constant. They don't change. The kinetic energy can be transferred from one billiard ball to the other one, or in a gas, one gas molecule to the other one. But the total amount of gas, kinetic energy associated with the gas, doesn't change at a given temperature. So there are two types of collisions that we have, and the one that we use to describe this is the elastic collision. So things bounce off of each other, kinetic energy is conserved. If I took two pieces of clay and I hit two pieces of clay together, what would happen is the clay, when they collided, they would deform. All right, that's called an inelastic collision. Now the kinetic energy, some of it is transferred into the energy required to change the shape of that type of clay. It's typically what happens in a car wreck. In fact, cars today are much safer for this very principle. Cars are designed to have crumple zones. I watched the news this weekend about a head-on collision the two cars hit. They talked about both passengers walked away. And the cars looked like accordions up to the windshield. And they crushed both of the cars. It happened in Bryan County. It was an article or a show on the news. But it doesn't always happen like that. But the fact that that much kinetic energy could be dissipated by reshaping the metal in the front of the car and keep it away from the passengers in the driver and the passenger, the people inside of the cab of the vehicle, is that's an example of an inelastic collision. We dissipated that energy in a different way. We changed it in its form. So kinetic energy was lost, transferred into something else. Now, if we think about how this concept of applying the kinetic molecular theory to the ideal gas law, how those two things match up, it actually works pretty well, because we know that the particles are constantly hitting the side of the container, and they have some force associated with them. We said earlier in the chapter, pressure is equal to force divided by unit area. So what happens if we increase the how fast they're striking that surface? It's going to increase the pressure for a given gas. So if we think about PV equals nRT, if we rearrange that look at the relationship between pressure and the number of gas particles, the more and more gas particles that are in the container, the more collisions are going to be occurring on the walls. So I expect the force to go up directly proportional to the number of particles and the pressure to go up. And that's what we see. These two variables are directly proportional to one another in the system. So if I increase the number of gas particles, it increases just like I expect it to. Also, based on what we see, is that we increase the temperature. They're moving faster. As temperature goes up, I expect to see pressure goes up as well. So the way that we view temperature, when we think of temperature associated with molecules, is temperature is a reflection of what the mass and velocity are, as represented by kinetic energy. And kinetic energy, this is a little fancier formula, but this is basically the same formula that I showed you a while ago. Kinetic energy is equal to 1/2 mv squared, where this U at the bottom represents the root mean square velocity. And it says that if we have a mixture of gases at the same temperature, they're all going to have the same kinetic energy. Okay, so all the gas particles on average are going to have the same kinetic energy associated with them. So what happens if you have molecules that have different masses, because there's a mass association with kinetic energy, there's this mass term in here, to have the same kinetic energy, the small molecules have to have a different velocity. If mass goes down, they're going to have to be moving faster. And the big molecules are going to be moving slower in order to have the same kinetic energy. So there's a relationship to it that's given by this equation. The average velocity, root mean square velocity, is equal to the square root of 3 times RT divided by the molar mass. So the velocity is proportional. So velocity is proportional to the inverse of the square root of molar mass. So I can actually put some level of prediction mathematically to know how much it would slow down or speed up if I change the mass based on that equation. So how can we realize this, or how do we see it? We know if the average kinetic energies are the same, what happens is that heavier particles have got to slow down. So this is a speed distribution at a given temperature, and how these different gases change their velocity distributions as a function of how much the molar mass is on the gas. Okay, so here are the gases we have are oxygen, nitrogen, water molecules, helium, and hydrogen. And you can see that their speeds change greatly. This is actually a room temperature plot. Around you right now, most of the gas molecules are oxygen and nitrogen, and they're moving with an average velocity somewhere between 300 to 450 miles per hour, or meters per second. That's the velocity units of this. That's very fast. Okay, they're moving at a really high speed. Now there are some small fraction of them that are up here moving more than 1,000 meters per second. That's faster than the speed of sound. Okay, some of them are going really fast. Now if I look at the different gases and I start comparing these different gases, what property varies among these different gases? So if I look at oxygen, nitrogen, water, helium, and hydrogen, what trend relates, what physical property relates the order that you see them displayed in? Molar mass. So the one that's the lightest is the one that's moving the fastest. So hydrogen gas with a molar mass of approximately 2 has the fastest average speed. And the converse of this is true. The heaviest gas, O2, with a molar mass of 32 grams per mole, is moving the slowest. But on all these gases, it's a distribution. They're not just going one speed. There are some hydrogen molecules that are absolutely cruising. You're talking about 3,000 plus meters per second. That's 2 miles a second in distance. If they didn't run into anything and the gas particles just going in a straight line. At the same time, you have a small amount of fraction of molecules that are moving much, much, much slower. Okay, as slow as 100 meters per second until they hit something. We know that gases move quickly. Somebody can walk into even a room this size, and if they have a strong perfume on or aftershave or whatever it is, you smell that in the entire room in a matter of seconds. Because these gas molecules are moving quickly and they're bouncing off each other, but the warmer it is of the day, the quicker and quicker they bounce off and fill the smell of the room. All right. So that's one of the properties that we have with gases. We can actually use this property of their velocities to determine molar mass. We'll talk about that in a moment. Now, one of the things I want to show you is that how it changes with temperature. So all of these plots here are at the same temperature. And if they're at the same temperature, they have the same average kinetic temperature energy. So at same temp. But if we vary the temp, those profiles start to shift a little bit. So here's an example of what happens when we increase the temperature of the gas. So as the temperature increases, the velocity distributions shift towards higher velocities. And so now it's looking at one of the gases, and it's looking at it at close to room temperature, 273 Kelvin, and it's down here in the 300 to 400 range as we talked about. If you heat that gas up to 1,000, the whole thing shifted in this direction. The other thing that happened to it is that it spreads out. So it's not just the fact that it increased, it spread out to a wider distribution. And if I keep going up higher and higher with the temperature, I'll see that here's 1,000 degrees, that it's even shifted up further than what it was before. And then also the distribution is covering a very wide range. At any moment, there's some gas molecules that are barely moving, and there's some that are absolutely cruising. Okay, that's 3,000 meters per second. If you do miles per hour of that, that's a very, very high speed. So what's changing when we change temperatures is that the velocities of these different molecules change, and they change away so that the kinetic energy, in particular, the average kinetic energy, stays the same. Okay, so here are the four most common gases in the atmosphere: nitrogen, oxygen, argon, and CO2. Which one is going to have the highest average velocity at room temperature? Answer it yourself question. Couple more. Three more answers. Okay. All right, we're all in. Survey says most of you think it is choice A. Choice B got quite a few votes. Nobody went with C, though. All right, so we just said the property it has something to do with is molar mass. Let's see what our correct answer is. It looks like it's A. Now let's figure out for those of you that didn't get it. Nitrogen weighs 28 grams per mole. Oxygen weighs 32. Argon's way up near 40, or sorry, near 30. So it's at 40. Yeah, and CO2 weighs 44 grams per mole. So the one that's going to have the highest average velocity is going to be the one with the lowest molar mass, and that guys are nitrogen. So that's the why A is correct on that one. Okay, question on that? All right, let's look at it from a different aspect. So of those four gases, which one has the highest average kinetic energy at room temperature? Three more guesses. Last one. Okay, curious where this is going. Most of you said D. I like that answer. So all gases have the same average kinetic energy at the same temperature. Okay, so That's the thing that changes. The velocities change, but the average velocity or average kinetic energy stay the same. Right, so that gives us some explanation of what we see in the ideal gas flow. Now, there's a term that we use called mean free path, and the mean free path of a gas represents the average distance that gas molecule can move until it collides in with another molecule or the container. That mean free path decreases as the pressure increases. The pressure increases because there's more molecules there. It could increase. Temperature wouldn't change it because it's just going there faster. It's not changing the distance. But more and more molecules are in a less reduced volume, means that it's going to be sooner until it runs into something else or runs into another gas molecule or the container in this. So the collisions, as they get smaller and smaller, I put more and more gas molecules in there. If I press this guy down on all sizes, means the collisions would be more frequent in the system. And the same if I put more and more particles in here, the collisions on the side that cause the pressure are going to be more frequent in it. So the mean free path is going to decrease with increased pressure in the system. Now there's two terms that we look at. They're called diffusion and effusion. These are physical properties of gases. They're not commonly used, but they're measuring two different things that are related. Diffusion measures how quickly a high concentration spreads out to a low concentration. And usually diffusion can be shown in liquids most easily because it happens so quickly in gases, it's hard to visualize. But I typically or sometimes will demonstrate this to a class. If you take a beaker of water, right, and you put some water in there, and I'll get some dye and put it in a syringe and gently put that syringe into the solution and inject just a small amount of whatever that dye is. And if I'm careful not to disturb the water, that dye appears as a drop inside of the solution, and I slowly pull the syringe out. That drop starts to slowly spread out. And over time, it diffuses because of the motion and interactions in between the molecules. It diffuses over the entire volume of the solution. And that takes, typically if this is like a 200 mils of water, that takes, depending on room temperature, anywhere from 15 to 30 minutes to occur. It's also related to how big the molecule is. You'll learn this if you take advanced biology classes, that big molecules can't move as fast as small ones. Okay, the small ones can wiggle through and go through much quicker. The big ones, they're kind of trapped in their space and they can't move very quick. Right, that's an example of what diffusion is. Effusion is an opposite process. It's how quickly a collection of molecules can diffuse through a small hole into a vacuum that's been produced. We use both of these. Effusion is actually the one that's easiest to measure. Both of these are related to the average root mean square velocity of a gas, and that velocity is related to the square root of the molar mass. So the velocity that we talked about, this mu root mean square, RMS, is proportional to the inverse of the square root of the molar mass. Right? So we can take an instrument that can measure this. If we have a gas inside of here and we open up this pinhole to let the gas out, how quick it takes the pressure in this gas to equalize between the two things, we can measure that pretty easily. It gives us a way to estimate what is the molar mass of that gas. So if I have a gas sample, I can put it in this device, open this valve up where this pinhole is, and look at how long it takes for that thing to reach equilibrium pressure. Where it's the same on each side. And that's a simple device that we can use to calculate how fast the rate of effusion is and estimate molar mass. Today, if you go to the airport and you're screened at the airport, So how many of you have flown on a plane in the last 2 or 3 years? Anybody ever had a wipe down test done? Whether wipe down your hands or your laptop, usually with something, or that you've been into a puffer. Puffers where you have to hold your hands up and the deal goes around you and blows little puffs of air out of you. What it's doing is trying to knock molecules loose that could be big thing they're looking for, or explosive. It also screens for drugs as well. But it takes those gases and runs them into an instrument, and it's an instrument that does a drift. So it takes those samples and it looks how long it takes them to drift down a tube. It's an example of doing a fusion, and based on that, if its drift is the proper time, and the alarm goes off, and people are going to drop down out of the ceilings and point guns at you and stuff. So it's that instrument that they use on those is an infusion-based instrument. It's called drift mass spectrometry that they're using. There's a more exact test that they have to do because there's a lot of things that can have the same molar mass and that this alarm would go off for, but it doesn't necessarily mean that it's an explosive or an illegal drug. It's just looking for classes of compounds to tell them they need to do a more extensive test. So Graham's law of fusion is one of the ways that we can follow these. What we do is simply set up this relationship. Remember on the previous page I told you that this rate, or this velocity, root mean square velocity, was proportional to the inverse of the square root of the molar mass. Okay, so what I have now is the rate for one gas, and its molar mass is on the square root of the molar mass is on the bottom. I have the rate of a second gas, and its square root of the molar mass is on the top. So these rates are measured with the instrument. It's something that we can determine. And as long as I have one known, I can set this up to determine the molar mass of something that I don't know. So basically, I calibrate it with a gas that I know its molar mass, and then I can use to find out what is the mass of an unknown gas with a given setup. It's a pretty simple measurement to do. Okay. So I told you this semester was a series of little white lies. Here's one of them. So we have to talk about everything we've done in the chapter has been talking about the ideal gas law. When we talk about real gases, we find that there's sometimes a discrepancy of the behavior between what we talked about with an ideal gas and what we observe in the real world. So we talked about how to do all these different things with PV equals nRT, but in particular at high pressures or at low temperatures, there's a deviation from what we see. The ideal gas law, based on the kinetic molecular theory, said that those collisions were elastic. There was no attraction between the gas molecules. The second thing that it makes the assumption of is that gas molecules take up no space. Remember we did that plot a couple of days ago where we changed temperature versus volume, and it went down and it went to a volume of 0. Now at temperature 0 and volume went to 0, that means the gas molecules theoretically don't have any volume associated with it. And even though they're small, there's something there. All right, so basically we have to correct for these in some way. And it's not typically a big difference that we see. As long as we're at lower temperatures and high pressures, typically the assumptions are the places that it's a problem. But if we'll look at how much the molar volume differs, we said that for an ideal gas it's 22.4. And it works right at 22.4 for nitrogen gas. And it's just slightly off, but one of the things that's off the most for is chlorine. Chlorine's molecular volume is actually 22.06. And we look at other ones that it's the biggest deviation we have, but whether or not that's significant or not, it depends on the calculations that you're doing. So let's talk about the why it's off a little bit. Okay, why it deviates. One of the problems is these gas particles really have some volume. Okay, so when we're at low pressures, argon pressure is identical to that of what the ideal gas predicts, or very, very close to it. But as I start to take the pressure up, now the molar volume of argon, and argon's a pretty decent sized gas, it weighs 40, it becomes greater than that of the ideal gas. So now the fact that the argon atoms themselves are contributing a little bit to the volume of the gas is what makes the pressure higher than that predicted by the ideal gas. The fact that they have volume and are occupying some of the space makes a contributing factor. So this graph shows you what happens if I took a cylinder and I started to compress it and compress it and compress it, and I look at the deviation, what I actually see versus what the pressure is. So here's looking at what the ideal gas would be in red, and in green is what happens with argon. Now you can see the pressure, this is in atmospheres, and these are hundreds of atmospheres. So if I'm up at 1,000 atmospheres, there's a pretty significant difference there. So over 10%, almost 20. But we don't do much chemistry at 1,000 atmospheres. And most of the stuff that we do in this world, okay, so down here to up to maybe 100 atmospheres at the most, the two things are practically identical. There's no measurable difference. But if you were doing chemistry of like what's happening inside of an explosive, where pressures are extremely, extremely high for short periods of time, you'd have to put some type of correction in for it. Right? There are times that you do these very non-traditional chemistries, and you have to account for that. If you become an engineer, you'll learn all about the fudge factors, as we call them, how you correct for these things. So when they realized that this difference occurred, way back in the 1800s, 1873, Johannes van der Waals, he came up with an equation that modified the ideal gas law equation to fit the behavior of real gases at high pressures. And basically what he put in is a fudge factor. So he said, instead of saying, if you saw PV equals nRT for volume, he realized that there had to be something that offset for the additional volume of these individual molecules or gas particles. So he said this fudge factor is just the number of particles times whatever this factor is to be. And that factor is going to depend on what the gas is. So if it's something like hydrogen, H2, in terms of molecular size, hydrogen's a very small molecule. Or if it were something larger, or like if it were going down to your largest gases, something like xenon. Xenon is much more larger in size. Xenon would have a much, much larger term for B associated with it than what hydrogen would have. And maybe we would have to increase that. But what he found was there was a term that he could call the van der Waals constant, B, that he could measure for different gases, and we could figure out how to correct this behavior that we have. If we're operating conditions, that's a problem. Now, the other thing that became a problem is that when they did measurements at high temperatures, things behaved just like they expected. The gases are nearly identical in behavior in terms of pressure to that of an ideal gas. The issue became when you reduce the temperatures and you slowed the molecules down. So what happens then is the pressure is less than that of an ideal gas. And what they found is that at lower temperatures, the atoms spend more and more time in molecules interacting with each other and less time colliding with the walls. So this makes the pressure a little bit lower than that predicted by the ideal gas law. And there's a typo in the notes. So right here I put collisions are not, and it says inelastic. It should be elastic. Collisions are not elastic like we think they were. They're not like pool balls completely, especially at low temperatures. They're a little bit inelastic, and they become more so when you reduce the pressure down. Okay? So there's a correction term that we have to put in this if we're in the world of low temperatures. Here's a plot of what's happening with pressure versus temperature. And you can see if you're at high temperatures up here, the two things get really close to one another. But if the temperatures go down further and further, and this is xenon, this is a pretty big gas, this is kind of a worst case scenario, that you could maybe get a 10 or 20% deviation when you start getting below room temperatures. So van der Waal came up with another term to modify the ideal gas law, and it's the A term they added. So on this one, it was the A term times the number of particles divided by the volume of the gas, and you had the square of that term. It's a little bit more complicated than the other one. And you subtract it so it corrects for the pressure term. So together, these two things come up to give us an equation that we can use to calculate for these non-ideal conditions to deal with real gases. And this is what we call van der Waals equation. Embedded in this is the PV equals nRT, but there is a pressure correction term and a volume correction term to offset those two non-ideal behaviors. So what you have to do in this equation is simply go look up the gas that they're using, whether it's helium or neon or methane, and you look up this A and the B term. And these become known terms in the equation. And everything else is a PV or nRT. Okay, so it's just a correction that we can apply to these. In more advanced classes or engineering classes, you'll do a lot of those types of applications. For what we're trying to learn in general chemistry, I just want you to hear this and know that we can correct for it. It's not, PV equals nRT is not a perfect fit for everything. It works very good for most molecules under atmospheric conditions and at near atmospheric temperatures, but it's not perfect. So the plot that we're going to look at on the next page is a plot of if we take and rearrange PV equals nRT, so PV divided by RT would be equal to N. So we plot the pressure ratio versus the pressure we see for 1 mole of gas, and we can see the differences between real and ideal gases. And in some cases, it's significant. In some cases, it's not very significant at all. So here's our ideal gas. In a perfect world, everything would be 1. Now again, this is going to some extreme pressures on this, going up to hundreds of atmospheres. But we can see something like water quickly deviates from the ideal and goes down here and drops down. And so does something like xenon. All right, so it has pressures below. And the fact that it's pressure below means that these are things are elastic. Or they're not elastic. They're sticking together when they collide. And they hang on to each other for a moment. And that causes the pressure to deviate lower than expected. And then you have the other terms that have volume, helium, and neon. They're always on the positive side. Sometimes this is just something we have to correct for. Sometimes it's not. Key thing is to recognize when. So that's what I want you to tell me. Based on what I've just told you, when do you have to correct for these non-ideal conditions using van der Waals equations? So I talked about 2 different times, both dealing with temperature and pressure. Tell me which 2 they are. Okay, 2 more. One person stepped out. All right, all in. Almost everybody says that it's choice D, and that is D, when it becomes a problem. Low temperatures, high pressures, so we don't have to deal with it. So if we're at something that's at in liquid nitrogen temperature, liquid nitrogen is 77 degrees Kelvin. All right, and if we're at a high pressure associated with that, that would be one of the conditions where would be the most deviation, and we would need to look at using the other A and B term in van der Waals equation. Most of the time, at atmospheric conditions, it's just something we don't have to deal with. Okay, that concludes the things that we've done in Chapter 6. So actually in the Mastering Chemistry, I don't know that there's... we'll do a couple of problems tomorrow, but there's very, very few problems left in the Chapter 5 Mastering Chemistry that we haven't done. So you can go ahead and get started on that. I think there's only like 3 problems for us to work at the end of the chapter dealing with the Chapter 5 Part 2. We'll do the pre-lab tomorrow, and then we'll go forward. But we're going to go ahead and roll right into start talking about chapter 6.
So after chapter 6, is that when our test?
We need to get as much of chapter 7 in there as we can, because our goal is to get through chapter 10 this semester. Chapter 10 is a really short chapter, and it ties directly with chapter 9, so those two will be kind of taught as one chapter. But ideally, I'd like to get through chapter 7 and a half to do that test. We'll see how close, how far we make. Now, one thing that makes it a little quicker, chapter 7 and chapter 8 are shorter chapters compared to the previous two that we did, chapter 4 and chapter 5, the biggest chapters we'll do this semester. Right, so the next ones are a little short. Okay, change of topics. Chapter 6 is looking at thermochemistry. So, again, here's some problems that I suggest that you take a look at. Ooh, down there. A little bit. There we go. It's in your advantage. You didn't make the test, the score you wanted on the exam. Start working those problems at the end of the chapter. You've got the problems that have solutions to them that you can look at the end of the chapter. Look at those, see how it works them out, and then start looking at these. Then, of course, do your own mastering chemistry. If you don't understand how to do it, go see the tutors. We've got tutors down there 4 days a week now, and a lot of students are going to see them. Come talk to me in my office hours. Figure out what you need to do better. All right, the outline for chapter 6 is we're going to talk about energy and some transformations that occur that we can utilize in chemistry. First law of thermodynamics, how we measure heat and work, relationships for reactions and how we measure that. We use the term delta E to describe that. Enthalpy and how we measure enthalpy of a reaction. This is one of the experiments that we'll do in the lab before the semester's over. And then some calculations using enthalpy. And then we want to try to tie all this into how we use energy in our daily lives. I mean, if we think about it in terms of our energy, everything that you use that makes your life nice, comfortable, different from what it was civilization 500 years ago is an energy conversion. The light switch that turns on your lights. The battery that starts your car, the internal combustion motor that drives you, those are all chemical reactions in one way or the other. The battery that's storing the energy in your cell phones. All of those are energy transformations that occur. We use these things from modern technology to the fundamentals of things like heating and cooling to get energy out of different reactions. One of the big debates today is how do we get the energy to sustain without burning fossil fuels? How do we keep CO2 concentrations from going up in the atmosphere? We're burning, even though we're becoming a little bit more energy efficient in the United States, and our population is pretty much leveled off, the rest of the world hasn't leveled off. Populations in some countries are continuing to boom and increase. We looked at that a few chapters ago, that world population chart. It's still on an exponential climb. As a society and as a world, we've got to figure out how can we make some changes that can occur. Can we go to wind power and do everything with wind power? I talk about this a lot in my physical science classes and alternative energy sources. What do you think is the downside to wind power? Other than a few birds are going to fly into these giant windmills and get killed. There's some ecological downside to it. But what do you see as a problem with wind power? Wind doesn't always blow. That's exactly right. There's a term that we use in Oklahoma called the dog days of summer. And you go out to any of the wind farms at the Arbuckles, or I'm going to think about the ones in Oklahoma. The ones in the Arbuckles are the ones at Weatherford, or go further north, go up to Buffalo. And there's was a new thing that was listed in the news a couple of weeks ago. Some companies putting in the largest wind farm in the United States it's going from the Oklahoma Panhandle, a straight line of wind farms going all the way to Tulsa. And it's going to be the largest continuous wind farm in the United States. They're going to put 10,000 units in or something like that. But the problem is, there are times the wind doesn't blow. Right? And if that's your sole source of your energy, all of a sudden you're without energy. Your air conditioner goes off, your lights go off, everything else. So while alternative energies like wind power are alternatives for us, they're not constant. And what that means is we can help reduce our dependency on fossil fuels, but we can't totally replace it. We have to have something different. So one of the other technologies that's becoming cheaper is photovoltaics, solar panels. All right, so they're learning to use less and less silicon. In fact, there was a new discovery patented, and the patent was announced to the public about 6 months ago. Now they can make a solar panel with 1/10 of the silicon that they used to. Now the solar panels that you used 10 years ago, the problem with it is that it took more energy to refine the silica and make that solar panel than the solar panel could collect in its lifetime. So solar panels, even though they were great to put in places that were remote, where it wasn't practical to run power lines to, or give you portable energy where you need it, solar panels until now have not been a acceptable alternative. I mean, you could have a completely solar powered house. Gore's house is a solar powered house. It took more energy to make those solar panels that he put on his house than he's ever going to get out of them in his lifetime. Was that a good alternative? No, the energy came from fossil fuels, so probably not. So how can we improve the efficiency of solar panels? How can we make them so they don't take as much energy to make? Then we can make maybe solar panels, photovoltaics, a usable alternative for us. So what's the downside to, if you think of solar panels? A negative aspect of them. Say again?
They're really expensive.
They are expensive to get enough power to do a home. There's somebody that's advertising on Facebook that somehow I became friends with, and it's about $100,000 to put enough solar panels out to heat a typical 2,000 square foot home.
So is it really not beneficial? Because they advertise that if you put those on your house, it'll pay for itself within like so many years, like 5 years or something like that.
Yeah, no. You'll get a lot of break with tax credits, and that's how the bulk of them are paid for. The tax credits are not guaranteed more than 1 year. So under the previous the last 20 years, we've been given alternative fuel and energy tax credits. So once you start making payments on your own home and you file your own taxes, you'll see that there's a place on your 1040 you can get a deduction for an energy saving solution. So if you upgrade something like a hot water heater to a high efficiency hot water heater, or you put more insulation in your house, you can deduct that on your taxes. So the biggest cost savings actually is a tax saving that comes into it. Cost wise, I mean, if you took a house that even took $50,000 to outfit with a solar package, what's a typical electric bill? Anybody seen their mom and dad's or got your own house? What's your electric bill run? $100? You live in a tiny house. Or a highly efficient house, 1 to 2. Okay, so probably closer to average to 300 to 400. If you're an all-electric house, so if you're paying for your electric in the winter, if you do a winter or full year average, and if you have OG&E, it shows you that. So you're looking at, if let's say it's 300, that's 3,600 a year. You're looking at least 15 years to recoup that cost. That's if you have no other expenses. So recoup it in 5 years, not going to happen. Now, if the panels get cheaper, if they can figure out how to make the panels 10 times cheaper, now you got something that's an alternative. But still with that, tell me a problem with solar panels.
The
Sun doesn't shine on them, they don't give off any energy. They're only good in the daytime. And their efficiencies diminish if it's bright sun versus a cloud blows over. Okay, so a cloudy day, their efficiencies drop 75%. So they're not foolproof. You can't use solar voltaic alone. We have to find combinations of. So if you look at things that are maybe more predictable, where does the wind blow constantly? Probably if you go towards the oceans, it's more consistent. So there are a lot of things taking, especially in Europe, they're putting wind farms out in the ocean, putting them 5 miles offshore. All right, and that way they're not on the. Some people say it destroys the scenic view set, and there's a big battle in Europe going on about that, on where they're going to put them. Engineers are going to strive to find new ways to answer some of these things for us. All right, so let's start talking about putting a few of these things to work. Here's some types of things that where we may see energy in the smaller scale. Those of you that, if you're a hunter, you may have used one of these things. So something like a chemical hand warmer. It works by a redox reaction that occurs for iron. They basically have iron filings in them. And then you break that package open and you allow it to be exposed with water that has oxygen in it. And as it starts to oxidize, it releases heat to the environment. Okay, so this reaction gives off heat. So you can get one of these things, break it open, and for about 3 hours, it'll keep it warm. You can stick that down in your coat pockets. If you're hunting, you can keep your hands warm or whatever the environment is. So what's happening here is how much the temperature changes in your hand depends on a lot of different factors. How big is this hand warmer? Is it one of these little tiny things, or is it a much, much bigger one? How big's your glove? The biggest thing that drives this is how much heat is released in this reaction. This heat term that's given off that's driving it forwards. Is it, if we want to think the unit of heat being joules or calories or whatever it is a small amount, is a large amount. Some reactions give off heat, some absorb heat in. So if you're an athlete and you've been doing it for a while, there's chances are you've had the opposite. Instead of a heat pack, you've had a cold pack. So they take these things and they break them open, 2 chemicals mix, and it sucks heat in from the environment. That solution gets cold, and then you can put it on wherever your injury is to cool it down a little bit. All right, so we think about chemistry, and the way that chemistry is important to us is that chemistry is a study of matter, and energy has a direct influence on matter. And there's a coupling between those two. We define energy in the fundamental way is the capacity to do work. Doesn't necessarily mean that you're going to do something with that. It means that there's the ability to do work out of it. And we define work as a force over a distance, so it has to involve movement. So energy is equal to work, and work is equal to force times distance. That's a physics definition. Heat is the flow of energy that's caused by a difference in temperature. So you have to have 2 things that are different temperatures to have a flow of heat. Okay, you're going from one temperature to the other. And we know that energy can be exchanged between objects through contact. So we usually think about it in something like a collision, but if 2 things are in physical contact with one another, you can have an exchange or a flow of heat between those 2. Heat can flow from one to the other or vice versa. Okay, so there has to at least be some type of collision. If I were to take an object and want to try to keep it hot. So let's talk about how a so what's these really expensive cups that you can buy to keep your coffee hot in? The Yeti. All right. So how does a Yeti cup work? And I've seen, I got a Yeti cup for a Christmas present a few years ago. You can put your whatever, hot or cold, in it. It works both ways, and it'll hold temperature for hours and hours and hours. Right? The way that it works is that it has a vacuum pool between the inner container and the outer container. If you cut one of these things open, it's nothing but, it's not air in there. The fact is, it's nothing in here. Okay, it's pump void. Right? The fact that there's no way for the heat that's here to be transferred to out here, and these heats are two different heats or temperature regions are isolated from one another, is the principle of how a Yeti works. And the same is true with those Yeti coolers. Right? You look at, I don't own a Yeti cooler. I'm more of a cooler. I'm an Igloo guy. Because igloos are about $30 at Walmart. Right? And every time I was at Academy yesterday, and we walked by and I looked at the Yeti that's $350. I can buy bag ice. I don't understand why they're that good, but maybe someday I'll win a Yeti cooler. I don't know. They work on the same principle. They isolate the heat inside from the outside using very, very high efficiency insulation. Something that blocks the flow of heat from the inside and the outside. Okay, so if we don't have direct contact, then we can't have a flow of heat in the system. So that's what good insulators do, is they try to stop that flow of heat from the inside to the outside. So if we start talking about the way that we can describe energy in a system and looking at that, energy can be thought of as something that an object possesses. All right, so there's so much of it there. And heat and work are two different expressions that objects can exchange energy with one another. And it can go either way. You can have heat and work going in and going out. So it can be done on a chemical system, or it can be given off by a chemical system. Hot packs, cold packs. It can go either way. It depends on the system that you're studying. So when we classify energy, there's a couple of ways that we can classify energy pretty simply. So kinetic energy is one of the ways. This goes back to what we talked about in the ideal gas law, said temperature is related to motion of molecules. So kinetic energy is the energy of motion that can be transferred in a system. Thermal energy is the energy associated with temperature. And if I look at those two things, the connection is kinetic energy is motion, and thermal energy is an expression of kinetic energy. So those two things have an integral tie with one another. If I reduce the motion out of a molecule, if I reduce the motion, what's happening to the temperature? It's dropping. It's going colder and colder and colder. Its thermal energy is going down just as well. Okay, so if I slow something down, as I drop the temperature, its thermal energy is decreasing with that. And we can think of playing pool again. This is the analogy that's in your textbook. You can have energy that's due to motion, kinetic energy. We can have energy transfer. Two balls collide. That's where you're doing work. One object is transferring a force to another one, and then that energy can be expanded off into more kinetic energy or heat in this system. So if we think of different possibilities that we have in just generic definitions, we said energy is the capacity to do work. And we think of that as kinetic energy, the energy due to motion. And with that, we have thermal energy associated with changes in temperature. The other option is we have potential energy. Potential energy is energy that's due to composition or the state of the matter. Right? When you get your gasoline, a can of gasoline, there's not a lot of kinetic energy in it. It's the stored chemical potential energy in that gallon of gas that's going to push your car hopefully 30 miles down the road. Right? And we have to do a chemical reaction to get that energy out. So when we think about potential energy, we're concerned with chemical potential energy that's associated to what are the connection between electrons and nuclei. What is this substance made out of? Now, if I think about just a classic hydrocarbon reaction, we talked about combustion. So let's go back and look at that one. So the simplest hydrocarbons, methane, plus O2, yields CO2 in water. All right, and if that reaction occurs, this thing certainly gives off a lot of heat. That's the classical way we heat our home with natural gas. That's the Bunsen burner we're heating reactions with in the lab. So the ones on the left-hand side, these two have stored chemical potential energy in them. Where it's being released as heat as the reaction goes forward. That's one of the problems with what do we do with CO2? All the energy's gone out of it. Okay, it's at a much lower energy level in terms of potential energy. To do something with CO2, to convert it into something else, we have to pump energy into it. Okay? We could sequester the CO2 that comes out of the smokestacks of the electrical power plants. We could convert it into something else. The problem is that it takes a lot of energy to do that. And it's not a positive payoff to do that at this point. Maybe if we learn a better chemical process, we can make that occur. We certainly don't know it yet. All right, so if we think about our potential energy and associating with just the simple views, and these are physical science concepts, I'm going to go over them quick. Potential energy is the energy that's stored in an object or associated with composition. That's the chemistry side that we think about. And if we think about gravitational potential energy, this is one of the simplest to see. You have potential energy stored in a cue ball based on its position relative to wherever you call the zero mark. Here's the tabletop. And as I release it, as it falls down, what's happening is that it's gaining kinetic energy, going faster and faster and faster until it hits the top. And then it can do some work down here. Maybe it can make another ball move. But that potential energy has been converted into a new form. So the gravitational energy is converted into kinetic energy, energy of motion. And that's a simple example of where we take and can convert between one form of energy, stored energy, potential energy, into energy of motion, and we can see that in a classical sense. Same thing happens in chemical reactions. You can convert potential energy that's stored into the energy of motion and release. You do that every time you start your car. It happens in a number of ways. The battery, when you turn your key on, some energy starts to flow out of your battery and fire up the electronics on the car. When you turn the starter, or push the button now, I've got old school, my key turns, you put it in and it's going to have to put a current in to turn the electric motor. Okay, so you got a chemical reaction that's occurring inside of your battery to turn your electric motor, which runs the starter, turns the flywheel, your motor starts going. And then you got a chemical reaction that becomes self-sustaining. The fuel that goes in, it's burnt, it expands heat and temperature, increases the volume of the cylinder, keeps your internal combustion motor running. It's an energy conversion, and we capitalize on those energy conversions. So what are the different ways we can convert between the different forms of energy? There's a lot of them. Here's the key things that we think about. Electrical. So we're associating with the flow of electrical charge. Most commonly, we're thinking about a single electron associated with that. We can add heat or thermal energy. To us, they mean the same thing. So that's associated with the kinetic energy associated with molecules. We can have light or radiant energy. And the reason we say radiant energy, we don't see all light. The only thing we can see with our eyes, as we'll learn in the upcoming chapter, is a section of visible light. So those of you that had a chemistry class before, what's the acronym for the guy's name that describes visible light spectrum? Some guy's name. Say again? Roy G. Biv. Okay, Roy G. Biv is red, orange, yellow, blue, indigo, violet. Okay, green is the G. Okay, that's the visible spectra that we see. But that's only a tiny portion of the radiant energy that can exist. There's higher energy UV light and cosmic radiation. There's lower energy infrared that we can't see with our eyes. Going below that, there's microwaves, and finally radio waves below that. All of those are energy transitions that can occur within atoms and molecules. Now, here's another one that we don't want to talk about much. We'll talk about it at the end of Gen Chem 2, but that's nuclear energy. Nuclear energy is one of the good and bads we have in society. The good thing about nuclear energy is that it produces no CO2 emissions. And if it's contained, it's the cleanest form of energy production that we can do. We have thousands of years versus of nuclear energy from uranium that's available that we can convert in a nuclear reactor. The downside to it is even when you have what you think is a very safe reactor design to it, as we learned in Japan in the tsunami that occurred a number of years back, Mother Nature says, maybe I'm going to let some of this stuff go. And that's what happened in Japan. Today we can trace the nuclear radiation to almost every point in the world that was released from that nuclear reactor in Japan. You put a nuclear reactor around a population. If you have a failure, it could influence in a very harmful way a significant population of people. So typically nuclear reactors are away from populations. Is there a nuclear reactor in the state of Oklahoma that produces electricity, as you may know? Anybody know where the closest reactors are around us?
Texas.
Well, it's about midway, so down by Austin, there's one. There's another one at San Antonio. Texas has 3 large nuclear reactors. And if you go out on I-40 and you drive west into Arkansas, you'll see another set that's there that powers Little Rock. So those are the closest one to us. In Oklahoma, we're not using those. We're going to pump the oil out of the ground until it quits pumping. All right. Chemical is the one that we use most commonly in terms of getting our major energy, fossil fuels, but we also look at that in our chemical reactions in terms of the energy that's stored in things like batteries, and that's a two-way street. Your phone discharges, you have to charge it back up. So we want our reactions to be reversible, go in both ways. Put energy in or take energy out. But with that, we're changing the attachment of atoms, we're changing oxidation states of molecules and atoms, and the key thing is we're changing the position relative to before and after. There's a number of different ways that chemical change can occur. Okay, so energy due to position or composition is which one? Probably the easiest clicker question other than I am here. Two people are not sure. One person's not sure. This man voted. There we go. All right. So everybody thinks they're here. All right. Whatever. So if we look at which ones we got, the dominant answer is D on this that you put. So energy associated with position is exactly that. It's potential energy in the system. All right. So we have a conversion that can occur between any of these. And that's how we capture in what we think of technological devices today, is to go things from like potential energy in a battery into kinetic energy, drive a car. Potential energy in a battery into our lights. It gives us electricity out of it. Potential energy into kinetic energy to heat our homes, our cooler homes. All these types of conversions, we can take the kinetic energy in the wind and we can store that back up through a wind generator or a wind turbine and put it in potential energy. Right? And we can store it back up, charge our battery with, or we can put it in an electrical grid. All of these types of things of going from energy from one way to the other are energy converters. And everything that you love about technology is an example of an energy converter. It's doing something with one form of energy and converting it into another to utilize it in some way. Unless today the thing you love the most in the world is art. About everything else is an energy converter. Whether it's your cell phone, your watch, your car, your TV, or whatever device you want to think about it. If it's a form of technology, it takes energy in one form and converts it into another. That's what energy converters do. All right, so law of conservation of energy says that we've actually talked about this one before in terms of form of mass, but law of conservation of energy says that energy can neither be created or destroyed. The total energy of a universe remains constant. So what happens is that when energy is transferred between objects, it's converted from one form to another. So if I take and look at an example of a ball in a spring. So at some point it's at the zero position. And if I put mechanical energy into it and I can press it down, as that spring gets compressed, it gets stored mechanical potential energy inside of it. If I release it, that spring decompresses, it shoots the ball in the air. That stored energy that was put in here has now been transferred to the kinetic energy associated with the ball that's moving off it. Kinetic energy is 1/2 mv squared. So kinetic energy is equal to 1/2 times the mass times the velocity squared. But now I'm giving it motion. That's the key thing. It's in motion. It's moving. It can do work if it strikes something. The total amount of energy, if we think about law of conservation of energy, however much energy that was input in here can exceed the output. So whatever this value is can't be greater than the kinetic energy that's associated with this. The kinetic energy can never be greater than the amount of work that I put into it, the energy that I put into this system. Okay, so we have to start defining what are we looking at in these things. So system versus surroundings, and this is critical, we understand the difference. So system is the material or the process that we're studying and with respect to energy. Most commonly we're looking at with respect to some chemistry. However, we can't take a chemical reaction and have it without a solvent around it or without air around it or some kind of container. So the surroundings is everything else that is in contact with the system, and it's where the energy exchange can occur with the outside. So energy goes in and out. It interacts and exchanges between system and surroundings and can flow both ways. So what we're trying to do in this chapter is we're studying this exchange of energy between systems and surroundings. We're trying to figure out where's the energy going? How can we make sense of it? So what we do is we compare the amount of energy that's in systems and surroundings, and we look at how it changes during transfer. Now, the law of conservation of energy means that whatever's lost somewhere has to be gained somewhere else. All right, or whatever's gained has to be lost somewhere else. And one way to think of it is think of it as your fuel gauge. All right, and the thing is that you can have fuel in different forms. Think of it, you've got two tanks in your car. Old vehicles, old trucks used to have dual tanks. You can switch between tanks. So if you want to think of it, if you got your system energy gauge and you got your surrounding energy gauge. So if I look at these, on this first one, it's half full in the system and it's a quarter full in the surroundings. And then some transfer occurs. What happens is this one went down. Right, so the one for the system went down by a quarter of a unit in this. But what happens is that quarter of a unit was transferred to the surroundings, and this one went up by the same amount. That's conservation of energy. So the energy is just transferred from the system, in this case, to the surroundings. And we can use that type of a quantitative aspect. What's lost equals what's gained to study these systems. Because I can't put a thermometer inside of a chemical reaction and measure the actual molecules. So even if I had a reactor where I was doing this methane reaction, and I'm burning this methane to produce CO2 and water, I can't measure the temperature of these individual atoms to see what the change is of the individual temperature. What I can do is I can measure the temperature of this whole system with including the surroundings as a container and look at how much the temperature changes. That's a process called calorimetry, which we'll do in the lab this semester. Okay, we got a good start into chapter 8. start doing some chapter 9. Those of you that are not doing your master in chemistry, it's going to come back and bite you. That's 20% of your grade. All right? Don't ignore that thing. See you tomorrow.